Anesthesia Machine series video. If you have not seen the first part, please look into that video first and then continue to this video to understand systematically. In this video, we will look into the breathing system, vaporizers, and the scavenging system in anesthesia machines. Let's begin with breathing systems in anesthesia machines. First, let's look into circle systems in anesthesia machines. A circle system improves the efficiency of anesthetic gas delivery by recycling gas that has expired from the patient and thus reduces the amount of fresh gas flow required. Fresh gas flow leaves the anesthetic machine and passes to the patient via a one-way valve during inspiration. As expiration occurs, the exhaled gases from the patient pass via a one-way valve to the APL valve, then onto the reservoir bag or ventilator. Before this, expired gas is mixed with the fresh gas flow and delivered to the patient. It passes through soda lime, which absorbs carbon dioxide. Initially, a high fresh gas flow is required in order to fill the breathing system with the desired mixture to equilibrate the system, after which a minimal flow of 0.5 liters per minute can be used. A circle system can be semi-closed or closed. In a semi-closed circle, the APL valve is opened and allows excess gas to be removed from the system and reduce the risk of barotrauma. However, the relatively high fresh gas flow allows a vaporizer outside circle, VOC, to be used, which can introduce a higher percentage and more precise anesthetic gas into the mixture. In a closed circle, the APL valve is completely closed. Although this is the most efficient anesthetic breathing system, it leaves little margin for error as the fresh gas flow must meet the exact patient requirements, and the soda lime must absorb all expired carbon dioxide. The minimal flow in this system only allows the use of a vaporizer inside circle to be used. A detailed description of vaporizers is beyond the scope of this article. One of the most important components of the circle system is soda lime. This is a mixture of 80% calcium hydroxide, 4% sodium hydroxide, and 16% water. It also contains a pH-sensitive dye, which indicates when the granules are exhausted. Soda lime granules are described as 4 to 8 mesh, which means that each granule will fit through a mesh that has 4 openings per inch, but not one that has 8 mesh. Let's look into components of breathing systems. A breathing system is made up of components that connect to the patient to the anesthetic machine, and is usually composed of some or all of the following components. First is the adjustable pressure limiting, or APL valve, and it allows a variable pressure within the anesthetic system using a one-way spring-loaded valve. At a pressure above the opening pressure of the valve, a controlled leak of gas is allowed from the system, which enables control of the patient's airway pressure. The minimum pressure required to open the valve is 1 cm H2O. A safety mechanism exists to prevent pressure from exceeding 60 cm H2O. However, be aware that pressures below this can lead to barotrauma. Second is the reservoir bag. It allows collection of fresh gas flow during expiration, which in turn minimizes the amount of fresh gas required to prevent rebreathing. In addition, it allows the anesthetist to monitor the breathing pattern of a spontaneously breathing patient. These are usually plastic or rubber and can come in sizes between 0.5 liters to 6 liters. However, the most common size in the adult system is 2 liters. Laplace's law states that pressure is equal to twice the radius divided by the radius of the bag. Therefore, as the bag increases, the pressure within it reduces. This is an important safety measure, as the expansion of the bag to accommodate gas limits pressure within the system. And third is the inspiratory limb, which allows passage of fresh gas flow to the patient for inspiration. The expiratory limb allows passage of expired gas from the patient. Although tubing length varies depending on the system in use, the diameter is of standard size, 22 mm for adult and 18 mm for pediatric systems. Let's know about scavenging and waste anesthetic gases. Scavenging is the collection and removal of vented anesthetic gases from the OR. Since the amount of anesthetic gas supplied usually far exceeds the amount necessary for the patient, OR pollution is decreased by scavenging. If a fresh gas flow-sized volume enters the breathing circuit each minute, the same flow must leave it or barotrauma will result. Scavenger and operating room ventilation efficiency are the two most important factors in reduction of waste anesthetic gases, WAGs. Scavenging may be active suction applied, or passive waste gases proceed passively down corrugated tubing through the room ventilation exhaust grill of the OR. Active systems require a means to protect the patient's airway from the application of suction or buildup of positive pressure. Passive systems require that the patient be protected from positive pressure buildup only. Another important distinction is that scavenger interfaces may be open to the atmosphere, or closed gases within the interface may communicate with the atmosphere only through valves, the older type. The different types of interface have clinical implications. Clearly, open interfaces are safer for the patient. From being relatively unknown 10 years ago, they are becoming almost universal on new equipment, so patient and anesthetist safety demands users' attention to the distinctions. At last, let's look into anesthetic vaporizer. Anesthetic vaporizer is a device generally attached to an anesthetic machine which delivers a given concentration of a volatile anesthetic agent. It works by controlling the vaporization of anesthetic agents from liquid and then accurately controlling the concentration in which these are added to the fresh gas flow. The design of these devices takes account of varying ambient temperature, fresh gas flow, and agent vapor pressure. Inhalation anesthetics such as nitrous oxide, halothane, isoflurane, desflurane, sevoflurane, most commonly used agents in practice today, are used for induction and maintenance of general anesthesia in the operating room. The volatile anesthetics halothane, isoflurane, desflurane, and sevoflurane are liquids at room temperature and require the use of vaporizers for inhalational administration. Nitrous oxide is already under normal conditions of temperature and pressure. All inhalational anesthetics provide amnesia and immobility, except for nitrous oxide, which also provides analgesia. There are generally two types of vaporizers, plenum and draw-over. First, we will look into plenum vaporizers. The plenum vaporizer is driven by positive pressure from the anesthetic machine and is usually mounted on the machine. The performance of the vaporizer does not change regardless of whether the patient is breathing spontaneously or is mechanically ventilated. The internal resistance of the vaporizer is usually high, but because the supply pressure is constant, the vaporizer can be accurately calibrated to deliver a precise concentration of volatile anesthetic vapor over a wide range of fresh gas flows. The plenum vaporizer is an elegant device which works reliably, without external power, for many hundreds of hours of continuous use and requires very little maintenance. The plenum vaporizer works by accurately splitting the incoming gas into two streams. One of these streams passes straight through the vaporizer in the bypass channel. The other is diverted into the vaporizing chamber. Gas in the vaporizing chamber becomes fully saturated with volatile anesthetic vapor. This gas is then mixed with the gas in the bypass channel before leaving the vaporizer. The second is draw-over vaporizers. The draw-over vaporizer is driven by negative pressure developed by the patient and must therefore have a low resistance to gas flow. Its performance depends on the minute volume of the patient. Its output drops with increasing minute ventilation. The design of the draw-over vaporizer is much simpler. In general, it is a simple glass reservoir mounted in the breathing attachment. Draw-over vaporizers may be used with any liquid volatile agent, including older agents such as diethyl ether or chloroform, although it would be dangerous to use desflurane. Because the performance of the vaporizer is so variable, accurate calibration is impossible. However, many designs have a lever which adjusts the amount of fresh gas which enters the vaporizing chamber. Let's wrap up with the soda lime jar. Soda lime is a mixture of NaOH and CaOH2 chemicals used in granular form in closed breathing environments such as general anesthesia, submarines, rebreathers, and recompression chambers to remove carbon dioxide from breathing gases to prevent CO2 retention and carbon dioxide poisoning. This was the last part of the anesthesia machine series. I hope you have understood the basics of the anesthesia machine. We tried to keep it simple so you can understand